Alright, so we have pendulum. You know the thingy that goes, just goes like that, right? So basically, what I think I want to do with the pendulum, I want to do some physics with it. So that might not make much sense. That's because I wasn't specific. So let me be specific. I want to see if I can find, right, a formula for angular acceleration as a function of theta. Where this is theta, right? So to do that, I think it'd probably be better if I found first tangential acceleration, linear acceleration, whatever you want to call it. Now, to do this, to find a tangential acceleration, I think I'm going to draw a force diagram real quick for the ball, I guess, on the end of this massless string. So, I mean, obviously we have the force of gravity, right? And, alright, so I'm sort of talking about forces, I'm going to talk about accelerations only, because, well, the mass will eventually cancel out if we just talk about forces. So I'm just going to talk about acceleration only, just the magnitude of acceleration, stuff like that. So we have an acceleration vector, right, pointing down with a value of negative g, alright. So to find the tangential acceleration, I want to break this up, right? I want to break this up into, let's see, an acceleration going this way. That's to deal with like the tension on the string and stuff, and an acceleration this way, right? An acceleration this way. This is the acceleration that we care about. This is the right angle. This is the acceleration that we care about. So that's great now, but like if we want to break this up, we should probably know angles. We should probably figure out what this angle is, right? Because only then we can do trig and find this. So now it's time to do geometry to figure out what this angle is. We see that this axis, I guess, is parallel to the direction of the gravity acceleration vector. So I think what I'm going to do is I'm just going to extend it like this, right? I'm going to have two parallel lines, and this is theta, this is also theta. I bet. So we know the angle now. So to find acceleration, right, A, or tangential acceleration, well, that's basically equal to, I mean, negative g, right, this is theta, opposite side, so negative g sine theta. G sine theta. Alright, that's great. So let's see. We know the value of tangential acceleration now. We probably want to find angular acceleration. So we know that tangential acceleration is equal to angular acceleration times the actual radius. In this case, we're going to call it L, right? Because we're going to say that the length of the string is our radius, and we'll call it L, right? So in our case, acceleration is equal to angular acceleration times L. But we know acceleration is tangential acceleration, negative g sine theta. So you get negative g sine theta is equal to alpha times L. We get alpha is equal to negative g over L sine theta. So that's great, but the actual question remains, why do I want to find angular acceleration in terms of theta? And I'll show you why. Because angular acceleration is the second derivative of angle, like it's basically a second derivative of angular position, if you want to call it, with respect to time. So we could say that alpha is equal to like the second derivative of theta, really. And then we can just set this equal to this, and we get a nice differential equation. So we end up with this. Alright. So that's pretty cool. If we could solve this, then we could technically, like, really be able to, I guess, know the position of the pendulum at any point in time, right? But the problem is, you can try to solve this for yourself. You're going to see that this is not really solvable by any reasonable methods. So then we have to resort to using other weird stuff like computers and Euler's method, I think, and other weird stuff. So, but getting this far is good enough, really, because then we can force the computer to do the rest of the stuff. But cool equation, nice derivation. Follow for more things like this. I might make a follow-up video on doing cool things with this equation. So yeah, follow for more.